Variance and standard deviation. There are many words that we use for the same concept. Variability, variance, volatility, dispersion, spread. They all represent how far apart the points in a distribution lie relative to the distance from the mean. Below you see 3 histograms of marks assigned by 3 radically different professors. All 3 have maintained an average mark in their classes of 70%. The first histogram is from Professor A, who believes fundamentally in separating sheep from goats. Evidently, half of his class consists of sheep, and they're assigned a mark of 50%. Whereas the other half are clearly goats, and they get a mark of 90%. The second histogram is Professor B, who takes a much more egalitarian view, without the need for examinations or annoying tests. He assigns everyone in his class the mark of 70%. And the last histogram, that of Professor C, looks a little bit more like a typical distribution of marks, with marks around 70 and 60 and 80 and 50 and 90 and so on, again averaging out at 70%. How do these 3 distributions differ? They have the same mean, but they differ fundamentally in the distance from that mean. The first distribution, the marks are very far from the mean value of 70. In the second, they're no distance at all from the mean, and the third is somewhere in between. They differ in terms of their variability, or their volatility, or the dispersion, the measure of which here will be the variance. To recap, in the first figure, the average distance from the mean is 20. The squared distance, 20 squared, or 400. And in the middle figure, the average distance from the mean is 0, and the average squared distance, also 0. Whereas in the bottom figure, the average distance from the mean is 11, the average squared distance from the mean, 210. That clearly ranks the 3 figures in terms of their dispersion. We very rarely use the average distance in elementary statistics. It's not very tractable mathematically. Instead, we typically use the average squared distance, which leads to the concept of variance. Variance and standard deviation. If a random variable x has expected value, e of x equals mu, then the average squared distance between x and its mean, mu, is the expected value of the quantity x minus mu squared. This is referred to as the variance of x, denoted var x, and often with the Greek symbol sigma squared. Note that it's something of a disadvantage that variance is in squared units. For example, if x is measured in kilometers, then the variance is in kilometers squared. If x is the weight of a random person in pounds, then the variance, the unit of variance, is pounds squared. To remedy this, we often use the square root of the variance, called the standard deviation, denoted by sigma. The units for standard deviation are now consistent with those of the original measurements. So again, if x were measured in kilograms, then the units for variance, kilograms squared, but the units for standard deviation would be identical to the original, kilograms. Simpler formula for obtaining the variance. Let's suppose the expected value of x is mu. Variance is defined to be the expected value of the quantity x minus mu squared. We can do some relatively simple algebra to get an alternate formula for the variance, simpler at least under some circumstances. We can begin by expanding the square x minus mu squared to get x squared minus 2 mu x plus mu squared, and then passing the expected value through, since the expected value of a sum or difference is the sum or difference of the expected values, we get e of x squared minus 2 mu e of x plus e of mu squared. Recall that the last expected value, e of mu squared, is the expected value of a constant, so that's just mu squared. The middle term, minus 2 mu times the expected value of x, is minus 2 mu times mu, or minus 2 mu squared. Combining those 2 terms, leaving the first term alone, we end up with e of x squared minus mu squared. So here's an alternate formula for the variance of x. The variance of x is the expected value of x squared minus mu squared. Here's some properties of the variance and standard deviation of a random variable. Suppose x is a random variable and a and b denote some constants. Suppose I'm interested in the variance of ax plus b, a linear function of x. Remember that the variance represents the expected squared distance from the mean. Adding a constant to all the values of a random variable moves the values over. So the addition of b simply translates the values of x to the right or to the left. It doesn't alter the distances between x and its own expected value. In other words, the addition of a constant has no effect on the variance. What about the multiplication by the constant a? The variance of a times x, when you multiply x by a, you multiply each of the distances between x and its mean by a. The squared distances are multiplied by a squared. And so the variance of ax plus b is a squared times the variance of x. The constant a gets pulled outside the variance and squared. The addition of the constant b in no way affects the calculation of the variance. If, however, we're interested in the standard deviation of ax plus b is a times the standard deviation of x. We obtain that by just taking the square root of the result in 1. Let's prove this. The expected value of x is mu, so the expected value of ax plus b equals a mu plus b. The variance of ax plus b is obtained by taking ax plus b, subtracting off its own expected value, and squaring that difference. And if we expand that, you'll notice that the b vanishes. We're left with ax minus a mu, the quantity squared. And when we square that, of course, a factors out, becomes a squared, and we're left with a squared times e of x minus mu, the quantity squared, which is, by definition, a squared times the variance of x. Of course, the standard deviation we get by simply taking the square root, and hence 2 of this theorem. In conclusion, adding a constant to a random variable doesn't change the variance. Multiplying by a constant changes the variance by a factor a squared. It changes the standard deviation by a factor of a. Alternative formula. For many standard distributions with the expected value equal to mu, we have another formula for variance, which is sometimes more convenient. The expected value of the quantity x times x minus 1 plus mu minus mu squared. We prove this by expanding e of x times x minus 1, leading to e of x squared minus x, and then adding on mu minus mu squared. That produces e of x squared minus e of x plus mu minus mu squared. But remembering that e of x is mu, and replacing it by mu, we get e of x squared minus mu plus mu minus mu squared, or e of x squared minus mu squared, which we recognize as the alternate formula for the variance of x.